Captain Mine, Illinois, 1988. The midnight shift is attempting to recover lost tonnage after a severe winter storm. Down on the pit floor, an electric rope shovel rotates toward the highwall. It is not a standard loading tool. It is a towering, multi-story steel fortress resting on crawler tracks the size of subway cars. The operator pushes the hoist lever, and a 90-cubic-yard dipper crashes into the fragmented rock, consuming over 130 tons of earth in a single 6-second pass. This is the P&H 5700. It was known simply as the Boss. In the 1980s, as haul trucks rapidly scaled up to 240-ton capacities, mine planners faced a critical bottleneck. Standard shovels required 5 or 6 passes to fill these new trucks, destroying the mathematical efficiency of the haul cycle. Harnisch-Fager Corporation, the builders of P&H shovels, answered with an act of sheer engineering audacity. They built a shovel with an operating weight approaching 8 million pounds, designed specifically to center-load the largest trucks on Earth in just 3 passes. But scaling an electric rope shovel to this unprecedented dimension broke the traditional physics of the loading face. The massive twin-leg dipper handle and the cavernous 90-yard bucket created immense geometric leverage. When this colossal steel bucket struck a dense, unblasted seam of rock at full crowd speed, the resulting kinetic shockwave did not simply stall the machine. It transferred millions of pounds of violent kinetic energy directly back into the boom and the revolving frame. How did P&H engineers design a structural platform capable of absorbing the impact of a 90-yard dipper hitting solid bedrock without tearing its own central pintle bearing apart? To force a 90-cubic-yard dipper through compacted earth, the P&H 5700 relied on a rack-and-pinion crowd system. This mechanism consisted of massive gears, physically driving the heavy twin-leg dipper handle forward, pushing the bucket teeth directly into the bank. In smaller shovels, this mechanical linkage was robust enough to handle the strain. But the Boss was applying thousands of horsepower against an unyielding highwall. When the bucket slammed into a hidden seam of solid sandstone, the dipper teeth stopped instantly, but the massive electrical crowd motors deep inside the machinery house kept spinning. This created a devastating mechanical crisis. The raw rotational torque of the motors violently bound against the stationary rack and pinion gears. To prevent the shovel from literally tearing its own boom apart, Harnisch-Fager incorporated a sophisticated, heavy-duty slip clutch on the crowd transmission. When the kinetic shock exceeded the structural limits of the steel, the clutch was designed to slip, burning off the excess rotational energy as extreme friction heat, rather than snapping the dipper handle. But this safety mechanism relied entirely on the veteran operator's physical connection to the machine. If the slip clutch failed, or the operator pushed the crowd control too aggressively into a blind seam, how did the immense electrical system react to a sudden, catastrophic stall? When the massive DC motors stalled against the unyielding highwall, the copper armatures stopped spinning, but the electrical demand did not. The motors instantly drew maximum locked rotor current. The P&H 5700 was connected to the mine's power grid via a heavy trailing cable running at over 14,000 volts. A sudden stall created an electrical vacuum that spiked the amperage draw across the entire local substation. Older shovels relied on mechanical contactors and Ward Leonard rotating motor generator sets to physically buffer this electrical shock. But the Boss utilized a solid-state electrical drive system known as Electrotorque. This system used massive thyristors to digitally convert and control the immense DC current. When the onboard logic detected a violent stall in the bank, The solid-state drives had milliseconds to electronically choke the power flow before the intense amperage melted the motor windings into copper slag or tripped the primary breakers for the entire pit. The veteran operator relied entirely on this digital safety net, feeling the deep, vibrating hum of the electrical transformers working behind the cab wall. They had to immediately reverse the crowd controllers, allowing the electronics to reset and attack the seam from a slightly different angle. But once the rock was successfully broken free and the massive bucket cleared the highwall, the shovel faced an entirely different physics problem. How did the mechanical swing system rapidly rotate millions of pounds of asymmetrical weight without ripping the center pintle out of the crawler frame? Swinging a 90 cubic yard dipper filled with 130 tons of rock required managing devastating rotational inertia. The upper structure of the P&H 5700 rotated on a massive swing rack, driven by multiple vertically mounted planetary gearboxes. When the operator commanded a swing, they were not just moving the bucket, they were rotating millions of pounds of steel machinery, counterweight, and payload. The true challenge was not accelerating the swing, but stopping it. If the operator rotated the fully loaded dipper at top speed and suddenly centered the controls to engage the mechanical holding brakes, the sheer momentum of the suspended payload would physically twist the massive steel boom and shear the teeth directly off the swing pinion gears. The mechanical brakes were designed only for holding the machine stationary, not for decelerating it. To prevent catastrophic structural failure, operators used a highly specific technique called plugging. They applied reverse electrical current to the massive DC swing motors to create magnetic braking force. It was an intense sensory rhythm. The operator had to judge the exact millisecond to plug the motors, allowing the immense structure to coast to a perfectly smooth, completely silent halt exactly over the bed of the waiting ultra-class haul truck. But dropping that volume of earth was a violent event. What happened to the suspension of a 240-ton haul truck when 130 tons of shattered bedrock fell from the sky in a single drop? Dropping 130 tons of shattered rock into the bed of a 240-ton haul truck is a violent transfer of kinetic energy. If the shovel operator opened the 90 cubic yard dipper too high in the air, the massive impact of the falling rock would instantly bottom out the haul truck's nitrogen-over-oil suspension struts, blowing the seals and potentially cracking the steel frame of the truck. To preserve the haul fleet, the veteran shovel runner had to lower the massive bucket deep inside the truck's dump body before initiating the release. This required perfect spatial awareness, ensuring the heavy steel lip of the dipper did not strike the sides of the truck. Once positioned, the operator engaged the dipper trip. Older shovels used a mechanical latch cord, but at the scale of the P&H 5700, the latch was operated by a dedicated electric trip motor mounted directly on the dipper door. The operator feathered the trip switch, allowing the heavy steel door to swing open, and smoothly hoisted the bucket upward as the material cascaded out. This technique, known as whipping the bucket, allowed the earth to slide rather than fall, absorbing the kinetic shock within the material itself. The truck's suspension compressed smoothly. But even with perfect loading mechanics, the shovel had to constantly advance to keep the highwall within reach. How did the operators physically tram a machine weighing nearly 8 million pounds across a soft, unstable coal floor without sinking it permanently into the mud? To keep nearly 8 million pounds from punching through the soft fire clay beneath the coal seam, the P&H 5700 rode on an enormous dual crawler assembly. The massive cast steel track pads were designed to distribute the machine's weight, reducing the ground-bearing pressure to roughly the equivalent of a human footprint. On paper, it was mathematically sound. In practice, moving this leviathan was a brutal mechanical endeavor. A tracked machine steers by locking one track and driving the other. When the boss executed a tight turn to realign with the highwall, the locked track acted as a solid pivot point, dragging thousands of tons of steel sideways across the abrasive, uneven pit floor. The friction was immense. The heavy steel pins connecting the track pads shrieked and groaned under the extreme lateral stress, a sound that could be heard for miles across the Illinois basin. To prevent shattering the crawler side frames or snapping a propel shaft, the veteran operators carefully planned their mining sequence days in advance. They engineered the cut pattern to ensure the machine moved in long, straight, parallel lines along the high wall, minimizing sharp turns at all costs. Every maneuver was agonizingly slow and deeply deliberate. But as the towering machine crept forward, it was physically tethered to the mine's infrastructure by a massive electrical umbilical cord. What was the fatal risk of dragging a 14,000-volt trailing cable through a busy, wet pit floor filled with jagged rock and rolling haul trucks? The trailing cable was the lifeline of the P&H 5700, pumping continuous high-voltage AC power directly from the mine's primary substation into the belly of the machine. But laying a thick rubber cable carrying over 14,000 volts across an active mining bench was incredibly dangerous. If a bulldozer blade snagged the line, or if a 240-ton haul truck accidentally rolled over it on the wet, rocky floor, the heavy tires could instantly sever the thick rubber insulation. A severed high-voltage line would cause a catastrophic arc flash, blowing the main breakers at the substation and potentially killing anyone standing within the immediate voltage gradient on the wet ground. To prevent this, the shovel crew utilized a dedicated cable tractor, a specialized bulldozer equipped with a hydraulic spool to carefully lift, loop, and elevate the line out of the mud and away from the active haul routes. Every time the boss moved to a new digging position, the cable had to be painstakingly managed. Once the 14,000 volts entered the massive revolving frame, it was stepped down by heavy onboard transformers to power the massive Electrotorque DC drives. But solid-state electronics, while highly precise, generate intense heat and demand pristine air to function. How did Harnisch-Veger engineers protect the delicate thyristors and digital logic boards inside a machine that spent its entire operating life completely surrounded by a dense, abrasive cloud of electrically conductive coal dust? Coal dust is incredibly abrasive and, under specific conditions, highly electrically conductive. If this fine particulate matter infiltrated the electrical control cabinets, it would cause massive, catastrophic short circuits across the exposed solid-state boards. To ensure survival, the entire multi-story machinery house of the P&H 5700 was transformed into a heavily pressurized fortress. Massive industrial blowers, mounted on the roof of the machine, continuously pulled ambient air through heavy cyclonic filter banks. These systems mechanically separated the heavy dust particles before forcing the deeply filtered, clean air down into the central housing. This relentless air volume created a constant, positive internal pressure. When a mechanic opened the heavy steel door to enter the machinery house, the rush of outward flowing air physically pushed against them, guaranteeing that no unfiltered coal dust could ever enter the electronic sanctuary. This purified air constantly washed over the thyristor cabinets, the massive AC transformers, and the heavy hoist motors, providing essential cooling and preventing thermal shutdown. It was a perfectly clean, climate-controlled environment floating in the center of one of the dirtiest environments on Earth. But the sheer engineering cost of maintaining this 8 million-pound, heavily filtered, solid-state giant began to weigh heavily on the industry. As the 1990s approached, what fundamental shift in mining economics signaled the end of the ultra-class rope shovel arms race? The P&H 5700 represented the absolute apex of electric rope shovel scale, but building an 8 million pound loading tool created an incredibly rigid production system. The boss could not easily walk away from a collapsing highwall, nor could it selectively sort through thin, complex seams of coal and waste rock. It was a blunt force instrument designed for endless, uniform digging. As the 1990s arrived, the economics of surface coal mining began to shift toward selective extraction and operational agility. European manufacturers introduced massive hydraulic excavators into the American pits. These machines utilized high-pressure hydraulic cylinders rather than wire ropes and rack and pinion gears. These diesel-powered hydraulic shovels did not require a 14,000-volt trailing cable. They could tram independently across the pit, attack a face from different angles, and selectively peel away thin partings of waste rock. While the early hydraulic excavators could not match the sheer, continuous operating lifespan of a solid-state electric rope shovel, their flexibility redefined the loading face. The industry realized that the ultimate loading tool was not necessarily the largest one. It was the one that could adapt to the deteriorating geology of the pit. The era of building exponentially larger rope shovels abruptly ended, replaced by fleets of highly mobile hydraulic machines. But as the era of the mega shovels closed, what became of the colossal P&H 5700 when the Captain Mine finally exhausted its reserves? The P&H 5700 was physically trapped by its own scale. When the Captain Mine exhausted its economical reserves and ceased operations in the late 1990s, the boss had nowhere to go. An 8 million pound machine cannot be driven down a highway, and the engineering cost of dismantling it, transporting the pieces, and re-erecting the massive steel structure at a new mine was mathematically unjustifiable. The world's largest operational electric rope shovel was cut down on the pit floor with cutting torches, sold for scrap metal, and completely erased from the Illinois basin. What the operating logs showed about how it had been managed, how the veteran shovel runners felt the terrifying rotational inertia, how they sensed the mechanical stall of the crowd system through the deck plates, how they whipped the 90-yard bucket to save the haul truck suspensions went with the operators when they retired. Some of it was written down in the form of informal shift notes and maintenance observations that someone thought to keep. Most of it wasn't. If this video gave you something real, subscribe. More machines, more mines, more of the operational reality that the trade show brochures never contained. Documenting the specific operational demands of the boss is essential to preserving the real industrial history of American surface mining before it is entirely forgotten. And if you ran one of these trucks, worked on one of these shovels, or engineered one of these operations, tell us in the comments. If you sat in the elevated cab of the 5700, what was the specific physical vibration that warned you the hoist ropes were nearing their tension limit? The most complete operating manual for these machines is in the heads of the people who ran them. Most of it was never written down. The highwall is gone. The pit is reclaimed. The machines that dig today are entirely different and know nothing about the massive, brutal physics that once dominated the coal seam.